All right, for this first example then, we're looking at a beam of particles with a 2e charge. Now don't forget that e is the fundamental charge, so it's 1.6 times 10 to the negative 19. And we're accelerating it through a potential difference. Now watch for that phrase there. If you see accelerated through a potential difference, that will always be this accelerator region, and we'll use, of course, then conservation of energy to solve for that. Now we're going to pass it through a magnetic field, and in that magnetic field, they curve with this radius of 11.6. And so what that means then is that we have the accelerator region over here. We're accelerating through the potential difference, and then we have then the detector region. Now these questions will only involve one or two of the sections. You'll never have all three, the accelerator region, the velocity selector, and the detector region all in the same question. So just look for which two then are going to be relevant to your particular question. So the first thing we can do is we'll sketch the electric field lines. That will of course be here because just the accelerator region has those electric field lines. So I have my positive terminal here. So this will be the positive plate. And then I'll have then the negative plate on the other side. Now your electric field lines, remember, go positive to negative. And so if I draw those electric field lines in to here, they'll just go in this direction overall. Now the next thing we want to look at then is what type of particle do we have? And because my positive plate is the one with the gap in it, I need to be accelerating then a negative particle, and then that one then will accelerate towards that plate and then head straight then into that detector region. Now the last thing we're looking for then is the path of the particle in the detector region. So this one we'll have to use our left-hand rule for this. Now it's a negative particle, so we'll use our left hand. You're going to put your thumb in the direction of the motion, so that's going to be to the right side of your page. And your fingers are going to be pointing down into the page, because that'll be your magnetic field. And you'll see then that your palm is pointing towards the bottom of the page. And so that's going to give us then this basically curved path towards the bottom of the page there. And so for the first one, we have in green here our electric field lines. We see it's a negative particle, and then we're curving downwards in that detector region. Now to find the mass of the particle, we're going to be looking at our accelerator region here, and then the detector region. So the accelerator region, if I start for that first, our accelerator region is always conservation of energy. So I'll look at my potential energy, and I'll make that equal then to my kinetic energy. My potential energy will be Q times V, and my kinetic energy is going to be 1/2 mv squared. Now I have two unknowns in this one. I don't know my mass, I don't know my velocity, and so there's not much more I can do with this one at this point. If I look at the detector region, here we're going to be doing then force equation with our centripetal acceleration. So I'll jump straight actually to the mv squared over r, so that's just m times the acceleration, and that'll be equal then to q, v, and b. And we'll see that one of those velocities then cancels out on both sides, and what we're left with then is mv over r equals q times b. And again, we have the same issue where we have an unknown mass and an unknown velocity. So what we're going to have to do for this one here is solve for a system of equations. So I'm going to isolate my velocity here. So we're looking for the mass of the particle, so I'm going to leave that in my equation, and then we'll use then we'll eliminate the velocity term by isolating it there. So then this one here will give me v equals qb times r over m. Now here I have my v squared, and I have my v, so I'm going to isolate v squared over here, and that'll give me then 2q times the voltage all over m. And so then that gives me v squared here and v. Now I could basically take the square root of this and then have two v's, but then my first step is just going to be to square it anyway. And so our better pathway here is just to square this right away, and then we'll isolate v squared in both. So I get q squared, v squared, r squared, all over top of m squared. And then what I can do is I can make then those two v squareds equal to each other. And so that'll give me then 2qv all over m is equal then to q squared, v squared, r squared, all over top then of m squared. Now we'll get a few things canceling out. This q and one of the squareds, this m and this m all cancel out. And then I can just isolate the m by moving it to the other side. And so I'll get m equals q, v squared, r squared, and then all over top of 2 times v. And that'll be then an equation I can use to solve for my mass. Now I just need to put my values in. Now remember we had a 2e charge from up here, so that's 2 times the 1.6 times 10 to the negative 19. So that'll give me 3.2 times 10 to the negative 19. That'll be in coulombs. Now watch your magnetic field. This is 75 millitesla, so we need to put that into Tesla. So 0.075, and now we're in Tesla. Don't forget to square that. And my radius, 11.6 centimeters, I need to be in meters, so 0.116 meters. And so do make sure that you're doing those unit conversions then as well. All of that then will be divided by 2 times that 70 volts then for my electric field strength. And when I put all of that in, oops, move up a bit. When I put all of that in, my mass then will be equal then to 1.73 times 10 to the negative 25 kilograms.